Good afternoon, everyone. Welcome to the mini school on quantum espresso. So maybe this is the time to have a quick espresso before the mini school starts, so that we are all awake and ready to listen to the talk. Again, I assume the lecture will be divided between Kingsley and Cecil that kindly agreed to share their wisdom with us. Yeah, and I see that the screen has been shared. So without further ado, Kingsley and Cecil, Cyril is another one. Cyril is another one. Is the guy who sends us the emails on Monday morning. Yeah? Cecil, please, you're welcome to start. Thank you very much. Sorry for
are you seeing the screen?
Yes. Thank you very much. It's clear and beautiful. Yeah.
Okay. So welcome back to the Quantum Espresso Mini-School. So I will be delivering part one, which is just a recap of what we did last week. So last week, you should still remember where we normally get our input files. So we start with the materials project, where we get our input files in CIF format. And then after that, we continue to materials cloud, whereby we generate input files that we normally use to run either on CHPC or on our Linux systems and stuff. So normally when it comes to running on the CHPC, we normally have the commands there. You normally SSH, always remember that you must run your calculations on Lustre, and also remember the project name that we are always doing. So last week, the case study we were doing last week was mainly on hydrogen evolution on Ti3C2. And you ended the class whereby you are calculating the absorption energies of hydrogen on top of Ti3C2, and also the calculation of the Gibbs free energy to establish whether the material is a good catalyst or not. So just a recap. So hydrogen evolution is just about the reaction that takes place in one of the electrodes in a fuel cell, for instance. And usually it is one of the main calculation that we normally consider, especially when you want to determine whether your electrode is a good catalyst or not. So usually the gold standard catalyst is normally the platinum. However, we are trying to seek for platinum alternative, hence this type of exploratory studies. So the picture on your right-hand side is for the pristine surface of or the slab that we are using for hydrogen evolution. And then on the left is whereby we are adding the hydrogen as an adatom. And in class, you are also shown those two basic, very important equations, the hydrogen absorption energy calculation and the Gibbs free energy calculation part. So for the hydrogen energy, the absorption energy calculation, you are just subtracting the energy of the pristine slab and the energy of hydrogen from the energy of the slab and the hydrogen. So this absorption energy calculation sometimes is often referred to also as the binding energy of the system. And we normally obtain them we obtain the energies from the calculations we run. The total energy calculation we obtain from Quantum Espresso that you can run either on CHPC or even on your local machine. Then towards the end of the class, you are introduced to the concept of the Gibbs free energy, which is usually the descriptor that is normally used to determine whether the material can be a good catalyst or not. So just a recap, a good catalyst for HER, the Gibbs free energy is normally approximately 0. But then for the one you calculated in class, you got like minus 4.23, which is slightly way above 0. However, you should remember that the system you considered last week, it was not yet fully relaxed or optimized. So in class, you did obtain these total energies that you see in the table below. And also you calculated the unrelaxed total energies of these systems. So going forward, as part of the assignment, you are supposed to to obtain these total energies for the relaxed systems. And here you should remember, when you are doing relaxation, you are only relaxing the atomic positions. You are not doing the variable cell calculations. And also on the configurations with the slab with hydrogen adsorbed on it, you considered 3 systems, which I show on top here. And then each of those systems, the total energies correspond to that second column that you see there. And from there, you are able to establish that the second row, the one written TI3C2 H center, HX top of C, that one was the best configuration because it was the one with the minimum energy, with the lowest energy. So you can refer to it as the lowest energy configuration. And then from there, it is the one now you used to fill in the calculations that you have on the table. So in the search for optimum catalyst, sometimes we don't just need to replace the entire electrode or the entire catalyst. Sometimes when you add dopants onto the material, you can improve the catalytic activity of the material. And this will be the subject of the class for today. So the image that you see on your right is the image that you were working on last week. And then in the image you have on the left, the red atom there symbolizes the dopant. And this dopant ranges from vanadium, chromium, it can be vanadium, chromium, or manganese. So what you do in this case, or what you will be doing in this case, is how to manipulate the input file that you used last week. And then you add the dopant closer or somewhere close to the adsorbed hydrogen. And then you calculate again both the adsorption energies and the Gibbs free energies. And then you see whether through doping, you can lower the Gibbs free energy that you obtained last week. So with that, let me invite Kingsley to continue with the demonstration part.
Hello, everyone. So I'm going to continue from where Cecil stopped. He's just giving like a very nice overview of where we were and where we are. And he mentioned that dopant is one of the ways we can lower the Gibbs free energy. We can also use strain to manipulate the Gibbs, to reduce the Gibbs free energy. But for the purpose of this class and this lecture, we'll stick to dopant. We can, like he mentioned just now, you can look at dopant close to the hydrogen, dopants farther away from the hydrogen. You can look at dopant energy, you can optimize your dopant formation energies, and you can, there are different strategies we can do. So he talked about single and double dopant introduction. I sent out a presentation earlier on before the class started on introducing this different dopant configuration in our system. So I'm just going to quickly go to my laptop and my desktop and show you some of these ideas we are trying to talk about today. So I'll go to my Linux, and then I will one second. So I'll do a brief explanation of the scripts I have sent to you earlier on today, just to tell you what we intend to do. Technically, a lot of these things for a beginner, I think you don't have to do too much scripting or complicated stuff, which I don't necessarily do always. So, okay, sorry. Trying to move my computer around. So I don't necessarily do a lot of scripting, but if you have like 1, 2, 3 different systems, it makes sense to do scripting. So you can get the right configuration. So we mentioned previously, so for this kind of system, because we already have our initial bulk configuration and we've optimized the bulk configuration, and that's part of why in the previous class, I said you should optimize those systems. So we've optimized for just one single atom of hydrogen absorbed at the surface. Now we can actually come here and look at different configurations. So if we can come here and say, okay, for this, we have a titanium site here. I just called that character. So something more simplified. So, okay, this I substituted as vanadium. So I call this character, and this is a very more elaborate script that I wrote. So if you see, you can actually have your vanadium, your titanium, your magnesium, your chromium, everything you want to substitute. But that's not the way we should go. So now I'll show you the way we should go. So previously we've said that for us to do this, we need to go to Materials Cloud. So I'll go to Materials Cloud. Just a bit of hiccup here. Materials Cloud. From the previous lessons, I haven't introduced something which I'll be introducing today. I can actually take a previously generated Quantum Espresso input file and use that file on Materials Cloud based on what I want to modify or what I want to generate. So I can do that on Materials Cloud. So, and maybe one of the reasons why you might want to do that is to download your pseudo potential files onto your local directory. So this might be one of the reasons why you want to go to Materials Cloud to modify your file. So I'm going to browse my local directory. So let's say I have a file called Espresso.scf that I created in Burai. I can open this file in Materials Cloud. And this is a Quantum Espresso input file. When I open this file, let's say I would say, okay, because I have magnetic atoms such as chromium and vanadium in my system, I'll choose a magnetic configuration. And then I would say fine, then I'll say generate my PWSCF file. So what this does is it allows for the appropriate pseudo potential you want to be created and all to be in one directory, and then you can download. You can download this folder. So when you've downloaded this folder, sorry for that. When you've downloaded this folder, you will get something called PWSCF. You get a PWSCF file. So I have already unzipped this file. In my PWSCF file, I can go in, and you all know how, you've all seen this before. What I did here was I introduced various substitutional dopant atoms in the system. So I would try and explain to you what I've done from Burai. So I use two different softwares, and you can just use one software to do this, but since we've introduced Burai in the lectures, and we've also introduced Materials Cloud, I want to show you what we've done. So what we've done here is open this particular input file. From this particular input file, I can click on an atom. So look at that, I've selected that atom. I can now rename this atom, say, to manganese. Okay, I think it's already manganese. So I can maybe rename something else. I click on that and I rename, say, to palladium. So now this atom is renamed already to palladium. From here, you can determine what kind of calculation you want to do. Say you want to do optimize, and then restart mode, I say no, variable cell. So variable cell is your VC relax. I say no. The method you want to use is BFGS for ion optimization. So I say, and then I subsequently now come I subsequently now come here and say, save as. So I can save this as I can look for an appropriate folder where I want to save this. Okay, just gonna cancel that. I'll save. So don't be scared to try and fail, because a lot of times these things fail. So I said save, so it's been saved. So I previously saved it, so I can resave the position, the directory in a different directory. So I typically save my file here, and I've got a lot of things going on in my workstation. So I'm looking for the appropriate file where I'm working on, and I was working on NITheCS, so I can call it whatever name I like. So like I mentioned, we save something with reasonable name, so I can say HER2 _ dot. So this project has been saved. If I go back to my directory, I would find this project and I can do those modifications I mentioned. So I'm going to quickly switch over to the slides. Someone you want to see the slides. So I'll quickly switch over to the slides. I hope you can see these slides now. So what I was trying to explain was how to introduce a dopant atom into the system. So you can either do it manually from Quantum Espresso, you can do it on Espresso, then you can do it on Vesta, you can do it on Burai. So the list of softwares you can use is quite endless. So I'm just showing Burai and Materials Cloud because these are the two we talked about in class earlier on. So next, I'll go back to the Linux platform so I can show you. So that you can actually see what we're talking about here. So on my Linux, so I downloaded that and I called it HER2 dot. So from here, if you see what it has created an Espresso SCF.in file. This Espresso SCF.in file contains magnetization. And then my atomic species are introduced here. I call them chromium, manganese, and palladium. In the class, we talked about vanadium, so I just changed that. And then we have the pseudo potentials we need, which are all here. The number of atoms is 41. So if you, and then the N type is 6, because I have 6 different types of species. So say I don't want, I only want manganese as my dopant atom. I can come here and delete chromium and palladium. So now I have 4 different types of species in my system. I can come here, I can come back here and now change. Number of atom type is 4. So a lot of these, because Burai does this for you, if you don't know what to do, I'll advise you to just use maybe Burai or another appropriate software to generate these input files. So because I know what I'm doing, I'm able to do this. So I can come back here. I substituted titaniums for manganese. You can see in your atom type, this is no longer titanium, this is now manganese. I would replace this with titanium back again. And because we are only interested in palladium, which you see here as PD, I would replace every other atom type in my file with the appropriate, because we're only interested in magnesium, I would also come and replace my PD with Mn. So I do not have any other dopant. Now you can save this calculation and you can run. Okay, we're not going to run it here. I previously copied, I created a script and then I sent the script to all the class before today. And the script is, since we are interested in single and double dopant, I call the script number, the first one was dope.sh. So this script allows us to create a single dopant file, allows us to create a single dopant. So it substitutes either chromium, vanadium, or magnesium here. And then I wanted magnetization in my system because I explained a priori that we are working with magnetic systems. So based on the fact you introduce static magnetization, if you do not do this, your calculation would have a problem. My number of atom type is 4. The reason is because we have titanium, we have carbon, and we have hydrogen. And then we introduced a dopant in titanium side. So now the number of atom type you have is 4. Your number of atoms, is 41. Your number of atom type is 4. So the flags N spin 2 says we should do a spin polarized calculation. N spin 1 says non-spin polarized calculation. So the default is a non-spin polarized calculation. So if you want to do a calculation without magnetization, you don't have to include static magnetization as well as N spin. Because we are doing a VC relax, I mentioned this in the previous class, we need to introduce ions and cell. Okay, the static magnetization, usually what we do is you introduce like a very small value. So if you look at my values, what I've introduced is this is 0.1, this is 0.3, this is 0.1 and 0.3. The system would evolve to the true ground state. You can also try, if you want to improve your convergence time, you can also introduce the static magnetization that is close to experimental value. But in a lot of cases, you wouldn't know for some systems, so you don't have to bother. So in the previous class, I talked about the number of ions in cell. The number of ions in cell is quite important. Why this is important is that if you're doing a VC relax or a relax calculation, you are optimizing the ions in your system. So you need to include that. If you're doing a VC relax, you're optimizing the cell as well, so you need to include that. For SCF, you don't have to include these flags. If you include these flags generally, so if you create a generic input file where you have these flags included, the code is smart enough to just ignore it, so that's a good thing. So coming back to the atomic species, you see that because I'm using the script and I call this character $, you can have the $. The $, will just substitute whether it's chromium or vanadium in your system. And it does the same. So I also did the same in the atomic positions. The K point, I reduced this to 4 by 6 by 1. And the reason why it's 1 is that the C axis is quite large and the cell parameters remain the same because we do not expect that to change. And I commented this part because this calculation, we hope to run it on the CHPC, not on our local computer. But if you've got a huge local cluster, you can uncomment that and run this kind of calculation there. So most of you have got your CHPC account. So right now, I'm just going to go to my CHPC account. So now I'm on my CHPC account. And I earlier on submitted this calculation thinking it won't take long, but apparently the parameters I'm using are quite tight. So based on that, the calculation is taking longer than anticipated. So if you look at here, okay, there's a question of how do you choose the static magnetization? I would explain that again. If you look at here, I was doing this manually because it's not very, probably it's not a lot of systems that I'm working with. So I can actually do it manually, but if you have to do more complicated systems, you should try and write a bit of script to do that. Part of the reason why I advise students to do this manually is that you kind of notice where you make a mistake or you get errors and then you are able to address your errors. So I created a file with h_v. So _v, I called it with h. It means that the system has hydrogen, and _v, it has 1 vanadium, and then .in. So in this, I will now show you the file again and talk about. So he says, how do static magnetization 2 and 4? How did I choose these values? So I got these values because I explained before, when we want to run this calculation, after downloading your zip file, you can upload your zip file to Materials Cloud, or you can use Burai. And then these softwares have already been optimized in such a way that they know what static magnetization you should use for whatever element you are interested in. So if you see, for one, we know that carbon is generally a non-magnetic system. So that is why it's 1.00 minus 1. And I also know that titanium would evolve to non-magnetic state in, if you look at titanium carbide, that's why it's also very low. So we made static magnetization for hydrogen and vanadium slightly higher, because hydrogen might evolve to a magnetic configuration based on the state you're looking at hydrogen at. So this is where it comes, like, if you have a little knowledge of the chemistry of the material you're studying, you can make accurate predictions beforehand. So for systems like this, because I'll just go back one step again, because I'm working in a specific directory, you can actually create different directories for every file you submit. But the good thing with Quantum Espresso is I can create my temp files all in one file. I can create all my out files in one file, just give them the appropriate naming. So I showed this in previous class, but it becomes more relevant now when you are looking at a lot of systems. So here I called my out directory v_out_d. So what is being saved here is all the wave function files and files that you get when you run your calculation. So for my system, since it's not yet optimized, this the out directory hasn't been populated. Let's see for the Chromium. Okay, still not populated. So the out directory will get populated with all this file. And if you work on a cluster or on your local computer, the files generated from the out directory are in gigabytes. So you run out of space quickly. And for most of you that have used any kind of computing software on the CHPC, you know that they always send out warning emails. So when you have this out directory or temp files, you can actually use a star, and you can actually say, okay, delete and delete your out files. So the eyebrow for hexagonal is eyebrow 4. For orthorhombic, I'm not sure, I think it's about 7 or so. So if you want to do that, I've showed you the Quantum Espresso documentation. So I can just go there now while you are here and send you the link as well. So the documentation, you can get Quantum Espresso documentation online. So it would be, so this is where you get your Quantum Espresso documentation. It's quite explained. So for your eyebrow, you click eyebrow, and then to tell you for your system. So for hexagonal is eyebrow 4. You have to include your cell DM. You have to include A and C. And then for orthorhombic system is eyebrow 8. So tetragonal P is 6, tetragonal I is 7, and orthorhombic is P. So continuing on where we are, okay, just a second. So call this with script. So I have to mind my naming conventions, but I create different names. So I just need to hammer on that scripting is not always important if you don't know how to script. You can just create your basic input files. And I also create my input files without scripting. But if you know how to script, then it's fine, because you can spend like 6 hours trying to write a script that would not work when you can just do the calculation in like 20, when you can make your input file in, say, 20 minutes or less. So we want to do a relax calculation. So okay, this is acting funny. So like I explained, scripting can get funny sometimes. So I want to see if I did the same wrong thing here. Yeah, so on my desktop, apparently I did it fine. On the CHPC, I did it wrong. So okay, yes, I can see what I've done wrong. So you see, I did not include the $sign here and the $sign here. So it's good it's good to make mistakes because part of the learning curve is making these tiny mistakes. then you get to see that, okay, I've done something wrong, and then you can quickly just address it. So I can run my script using that, and then I say for the doped cases, so I have rerun my script, or you can say sh, which is shell. If you are using, depending on what kind of bash environment, whether you are using TSH or CSH, you can, it will give you different, you have to use different commands to run your script. So if you want to use, if your script has, you need to change the command to use an executable command to run. So I'll come to the first file again. So if you look at this, going back, okay, you'll see this is already changed to vanadium, and my out there, I have a problem. So it's always nice to go back and check. Okay. The computer is quite slow to respond to my commands for now. So I'm going to replace. So I'm just running the calculation. Funny enough, my script for changing the out there is sort of misbehaving. I think just need to figure out what's going on here. So, and I wouldn't be too much alarmed because I have done this before, and it's the advantage. When you've done stuff before, you can always just go back to what you've done before and check what you've done or what you're doing wrong. And so this is why there is a lot of online resources or people you can talk to whenever you're doing computational physics. And that's part of what we're trying to introduce in this class, that you can actually get mistakes or something. So it's not the end of the world. And so this is why I also say that you don't want to invest too much time in trying to write the script that would end up not working. So I did this previously. So this was what we used. This was the script I gave you guys earlier on to optimize your system. So maybe it's the positioning, but I need to figure out why this particular case it's not working, but I think this should work now. Say temp. And I want to put in, I like to put an underscore. Part of the reason why I like to put an underscore when I create names like this is that I can, it allows me to also do another kind of scripting when I need to delete files. So when you need to delete your files, then it's also easy to write a script that helps you do that. Keeping my eyes on the time. Okay, so that problem is rectified. You can see I have .temp_m, so it means that my input file works properly, and you can actually submit this input file. I already have something called QE, so I can, my project name on the CHPC is math. So I'll just cancel this first because I just need to copy one of these names. So my project name, I know, but I gave you guys all project names which you can use to run your calculation. And this script reads an int file. You can also create a submission file for this for this. So I would say 1 hour because I don't think it's going to finish running. Okay, I think I wrote the wrong thing. I don't think it's going to finish running at the end of the calculation, at the end of this meeting. So yeah, you wish to submit, no. So it created a piece of file. So when you do something wrong, you always get an error somehow. So my number of nodes was not properly created because I made an error in my QSOG. So I would rerun that again. So sometimes I generally prefer if someone is working on this system, check your input file before you click submit. Your submission script before you click submit. The reason is because you don't want to wait on the queue for like an hour or so, only for it not to work. What am I doing? Okay, sorry guys. I think I'm getting tired. So, 166. Paste here. PW. Number of nodes, 1, full time, I'll just say 48. Email address, no. Okay. So I don't think it's my fault. I think it's something that happens with the CHPC. So this Espresso 6.7 appears and disappears sometimes. So I'll just use the normal one we've been using in this class. And PW, number of nodes, 1, all time, 48, email address, no. Okay, the CHPC is having some problems. So, okay. But let's see what was created. And this was created previously. So you can't run this file, but it's okay. It's a problem from the CHPC side, not from my side. So sometimes you have your calculations that you run and then they kill them because of load shedding or whatever reason. So I'll go back to the main presentation and try and explain some other concepts before we run out of time. So I was here on showing how you can introduce single and double dopants. So I think I spent a lot of time showing single dopants. So, I mean, further work you can do is prepare a table for single dopants and prepare a table for the double dopant. So all we are left to do is to do the submission with the script. The script should work fine. I mentioned in my email that I didn't change the pseudo-potential names that I sent to you, and I did that intentionally. So when you run, you will find an error in the script, which would force you to take note and try and modify that. So next, after you've obtained your energies, so when you run this calculation, you are doing the calculation for the pristine system, which is EP. So you determine the total energy. Then you determine the total energy for the system with the dopant. So for these systems now, our pristine system is no longer the system without hydrogen. It's still the system with hydrogen adsorbed, and this is the dopant. We have our dopant on the surface, so that would be ETM. The chemical potential, you need to determine the chemical potential for titanium and the chemical potential for the dopant. This is pretty straightforward. You just need to look for titanium in its ground state and do a relaxation calculation using the same pseudo potential as you've used in this system that you are evaluating. And then you do the same for the dopant you are considering. And then you can calculate the pseudo potential. I think I elaborated on it. We've elaborated on it in some papers we've published. So ETM of the dopant. So now this would give you the dopant substitution energy. So from this dopant substitution energy, you can now determine, I'll just jump to, from the dopant substitution energy, the dopant substitution energy is also our formation energy. So it's just different names that is called. You can call it the formation energy for the dopant or the dopant substitution energy. And you can look at it in the titanium rich condition and the nitrogen rich condition. To avoid complication, I didn't show, I won't discuss this, but you just keep in mind that these conditions exist. You can look at this paper, which we've seen in the previous class for further reference. So I'll go back now when we consider more than one dopant in our system, so we can have like a titanium dopant, you can have a palladium dopant or a palladium or a nitrogen vacant or carbon vacancy or nitrogen vacancy, or sorry, not nitrogen vacancy, carbon vacancy. So if it was if you have two vacancies, so it would be ETM TI minus dash TM of whatever of TI. So I'll just write on my screen. So you would have something like E bracket TM TI minus, you are substituting, let's say we call that other transition method TM as well, TI bracket. So you can have something like this, and then this will be in subscripts. So this is the more ideal notation to use. So you can have different kind of dopant complexes on your surfaces. And part of the reason why we introduce this dopant complexes is to try and make experiments. So you can do different dopant complexes and determine the most optimal dopant configuration. So going back, and then from here, you can substitute these dopant complexes you've introduced in your surface, and then you'll be able to get the binding energy. The binding in the individual dopant complexes, the energy of formation for this. The reason why you do it is because you actually want to find out if the system will form or not. So if for these configurations we considered in this study, we found out that they are all negative. And the implication is that the formation of these systems are feasible. And if you look at, if they are positive, it means that they are not feasible. Now, if we look at let's say this dopant configuration and then vacancy, for 1, 2, 3, you find out that these values are all positive, even in the titanium and the nitrogen-rich configuration. This is telling us that these dopants would not form. For me, or if it forms, it will take in a lot of energy. So you're looking at that amount of energy. So on the realistic side, you might decide not to calculate the binding energies any further for those configurations and motivate on that reason that this would not form. But because this was more like a holistic study for students' thesis, we went ahead and we did something like that. So take note of when you need to do some things and when you don't need to do that. So I'll go back again to the CHPC, and hopefully it's working now. Right. Okay. So we use this to create our input file, and 1math1366. Did I change that? Yeah. It's TI3 C2 underscore MN E. We want to do a PW calculation. Number of nodes, let's say 2. I'll say 24 hours. I'll say no. Okay, then no. Okay, now so like I said before, sometimes this can be, you just have to try again after a while, and then you would have the right thing. So if you look at our submission script, we selected to run on 2 nodes. When you use 1 node, your queue you submit on is the SMP, but for 2 nodes it's normal, and then it will take a longer time to run. But this calculation, hopefully I haven't exhausted my quota with my other running jobs in the CHPC. So this would, you can see, so it's submitted. Then you can check your running jobs. So you see my job is on the queue now. So it's not yet running. So I'll go back to the presentation now, just to, all right, back to the presentation. I have like 2 more slides, so we're doing good on time. So I've explained that, I've explained the binding energies in this previous slide, that the binding energy is important when you do more than 1 dopant. You need to evaluate the binding energies, whether this dopant configuration would form. The formation energy is important when you do 1 single dopant, so you can call it the dopant substitutional energy or the formation energy for your system. Now, I brought the slide again to highlight that this is one of the key important things for HER. You need to calculate your dopant hydrogen absorption energy. Then from here, you need to evaluate your Gibbs free energy. The more advanced you get, you can actually calculate your 0-point energy between the difference between the gaseous and the adsorbed hydrogen. And you can also do that for your entropy of formation as well. When you introduce this, you would get your Gibbs free energy. But for a lot of systems, we know that this column here. So I'm just going to say fill color, no fill. Okay, I think I'm sorry, I'm supposed to say shape, no fill. So we know that for a lot of systems, this energy here, so I can call that, just need to get my text box again. I can call that whatever I want, but usually we'll try to use names that are intuitive, so I can call that a correction. So it's usually around 0.24. So if you determine your DFT energy, you can actually just introduce this correction factor in your adsorption energy, in your hydrogen adsorption energy to evaluate your Gibbs formation energy. So far, are we all good? Yes. All right. Now, like I explained previously, we evaluated all of the system, both the stable and the non-stable system, because we needed to do a more exhaustive study for this work. And fill, shape, fill, no fill. So we evaluated everything. But in a lot of cases, you can say, okay, based on this, so in our conclusion, we were able to conclude that only 1 or 2 systems are better than the pristine. So if you look at this case, we know that for all the cases with your substitutional dopant, they are all stable. And so if you consider, you find out that ion substitution in this system improves the dopant configuration, improves the HER condition for this system. So you get 0.34, which is not exactly optimal, but close enough to the optimal value of 0. So at this point, I would ask if there's any question before I go back to the CHPC on the presentation so far. Okay, no questions. Okay, now I'll just share a new screen, and that would be my CHPC screen. I think that's what is being shared. All right, so I'm going to go to the script of, I'm going to go to the script of having double dopants in our system. So we can complicate this script as very different ways. Okay, someone says, how can we do for the reach system? So I'll show you in just give me 2 minutes. So we can complicate the script as much as we like. Did I do this? Okay, no, sorry. So yeah. So I'm going to come here and correct my previous error. And I think I can do this as well. I can do this as well. And so if you look at what we have here, now in our atomic positions, I have introduced the first character and the second character I want to change. So we can do like, and then because I'm changing the same thing, I want to have the same kind of dopant. I introduce the same substitutional, I introduce the same stuff. If you want to do 2 different kind of dopant configuration for different stuff, you can say, okay, I can do this. So I don't think I would just show too much of this, but I can say this is character 1. I can also expand on this and say character 1. So this will be a bit more robust, and then this script will be a bit more robust. I can come here and say character 1. At this point, I would have to introduce the other pseudo potential as well. But now this is where the conundrum comes. You don't want to have 2 different atomic species or different number of species. So you want to actually keep it as simple or as less complicated as possible. So I wouldn't do this. I would rather use an if-else statement to do my, to write this script. So now let's go back. It says, how do we do the rich and the titanium rich and the titanium, you can do for the titanium rich and titanium poor condition. Now, how do we do this? We can do this, I'll just try and, we can do this by considering titanium. Your chemical potential for titanium in titanium rich condition would be determined considering titanium in its ground state. So you look at titanium bulk, you use that to determine the chemical potential of titanium. For this kind of system, because you're looking at, let's say, titanium carbide, not titanium carbide, you're looking at titanium Ti3C2, so which is a carbide of titanium. You would have to take that configuration of titanium carbide you are interested in, calculate the energy, and subtract the energy of titanium, and then you'll be able to get, okay, that's titanium poor condition or titanium rich condition. You do that also for nitrogen or for whichever system you are interested in. So this just complicates slightly what you have to do, but in principle, you just have to calculate 1 or 2 extra total energies. Yeah, I do hope I've answered your question. So I'm going to go back to just, I'll just share the slide one last time, and then we can end for today. Okay, this is the old slide from last week. Okay, I hope you can all see my screen. So at the end of this school, I want to draw your attention to the various things we've looked at. We've looked at how you can get your input files, how you can generate input files in a very realistic and simplistic fashion. I've also tried to complicate it slightly by introducing how you can use some slight form of scripting to generate your input files. You can also go to the Quantum Espresso. You can also go to Quantum Espresso forum to be able to create your input file by hand on command line using your choice of editor. For hydrogen evolution reaction, we have shown that the important things are the adsorption energies and the Gibbs free energies. And this you can calculate using Quantum Espresso. You can determine things like density of states, which I mentioned that you should determine in the previous class, and then you can do that also. These are all, you can get most of these input files following the different procedures we've introduced at the end of, in this school. And last but not the least, I would like to thank NITheCS for this forum. I would like to thank all of you for your attention. I would like to thank my fellow presenters, Cecil and Francesco, for the opportunity. Thank you. Yeah.
Yeah, thank you very much, Kingsley and Cecil. That was a fantastic school, and it will be very interesting to see if in the next weeks the CHPC notices an exponential increase of Quantum Espresso activities. That would be very nice. Yeah, and in case maybe maybe next year we can do a refresher course. Because every year there are new people coming in the system, and or we could do a more advanced course. Yeah, so there is potential to refine the skills in Quantum Espresso for many people. Yeah. So thank you very much to both of you. It was a fantastic school, and we will keep advertising the recordings of the videos on our YouTube channel, so that people that didn't have the opportunity to attend live might be able to profit nevertheless from your your lectures. So thank you very much. And just a quick reminder, if you are happy to share the last slides with me as well, we will upload them also on the website next to the link to the videos. Yeah, no, perfect. Thank you very much. Thank you.
Okay. All right. Thanks very much. And
and thank you to all the participants for being so engaging and bombarding the two speakers with questions in the chat. That it's very nice to see that even these virtual meetings can be quite interactive. Yeah, and I'm sure that Kingsley and Cecil will be happy to answer your question if you drop them an email in case you are stuck at the CHPC or in Quantum Espresso. Yeah. So again, thank you very much, everyone. Thank you, Kingsley. Thank you, Cecil. Sorry, for some reason I'm always tempted to say Sil. Yeah, and thank you very much to all the participants. Thank you very much. Have a good afternoon. And probably tomorrow we will send out, or the day after tomorrow, the advert for the next mini school in June, and that will also be a very interesting topic. Yeah. So thank you very much. I hope to see most of you again in June in the mini school. Thank you. Thank you very much.